thank you very much for the introduction. My name is Shaukat Ali, and I work at Simula, which is located in Oslo, in Norway. And today I'm going to talk about some real-world applications of quantum extreme learning machines, which is one type of quantum machine learning algorithm. So before I go into the detail, I would like to highlight that in my department, we focus on three key areas, which is quantum computing, artificial intelligence, and software engineering. And the important thing is that we look at also the intersection of these three fields. For example, how artificial intelligence can be applied to enhance quantum computing, for example, for software development, for circuit compilation, transpilation, and so on. But we're also looking into how we can enhance classical AI algorithm with quantum computing. So this would be the key things I'm going to discuss in my talk. So first of all, I will talk about quantum extreme learning machines. And I will say that how we applied them into one industrial application and two real-world societal applications. And then I will also see how this particular quantum machine learning algorithm is being affected by current hardware noise, specifically in superconducting quantum computers. And then I will also talk about some other future applications that we are looking into in my department. So the first case study I'm going to talk about is built by a company called Orona. They are located in the north of Spain, and they are quite well known in making industrial elevators. And the company makes the entire thing. They make the software, they make the hardware, they simulate, they do different kind of testing, such as software in the loop, hardware in the loop, and real-world testing, and so on. And for them, it's very important to make sure that the elevators are safe. And they also want to make sure that they deliver good quality of service, because this is one of their key aims. And they also deploy different kind of simulation software. For example, this is one of the software they deploy. So for example, to simulate passengers, different kind of buildings, to do performance analysis, and so on. So what we did in this context is that we worked with them, and they already applied this classical machine learning to support regression testing of their elevators. So what we wanted to try that how this quantum machine learning would work if we try to replace the classical machine learning with a quantum extreme learning machine to assess its performance, to see if it can bring any benefits. So this is the first industrial application that we work with. But then we also work with one of the public sector in Norway, which is called Cancer Registry of Norway. And it's a population-based registry, and we know that Norway is a small country. We only have about 5.5 million people. And this registry has about 1.7 million cancer cases registered in it. And it's about 98.6% complete cases of, what I mean is that when a person gets a cancer, his record is established, then it's a complete history over the life of the patient about different reports from the labs and the hospitals and so on. And I would say that this is one of the most comprehensive cancer registries in the world, established in 1956, and it's being very digitalized since long time. And to maintain all this data and continuously evolve it, we have built this system, which is it's a very complex socio-technical system, because it has to deal with different kind of people, for example, patients. Then it is also connected to the hospitals, different kind of labs, and it also produces different kind of statistics, which is read by, for example, politicians to make different kind of funding decisions. These are read by hospitals and so on. So it has a lot of different set of, you can see here is different kind of people involved. And within this cancer registry here, you can see that there are specialized people with the medical expertise who implement part of the system based on the medical knowledge and so on. So what we did is that since it's a very complex system and it's a live system, it means that data is continuously coming, it is being processed and so on. So together with them, we built this system, which is called Cyber Digital Twin of this system. And this is based on the concept which was proposed by Facebook a few years back. So it means that we cannot just run the tests on the real system because it can interfere with the performance of the system, correctness of the system. So what we did is that we built a complete simulation system, which means that you can run all the tests, all the simulation that you want to do on the twin instead of the real system. And so so different parts of the system are being simulated into different things. For example, there's a behavior of our medical coders who code different kind of rules in the system. And then we have hospital professionals and so on. So the idea is to reduce the interaction with the real system so that we don't interfere and don't interact with the behavior of the real system. So this implementation of cyber digital twin has a lot of machine learning components to make different kind of predictions and so on. So the aim of our project is to try to replace some of those classical machine learning algorithms with a quantum machine learning algorithm to see how they perform. So far we haven't replaced everything with quantum machine, but we have replaced a few things there. And the third real-world societal application is about Oslo City's healthcare department. So it's also a city and it is responsible to provide healthcare services to its residents, just like myself. And they build a very complex ecosystem of healthcare devices deployed all over Oslo. And our project is about to improve the testing of those devices which are deployed in the whole system so that the quality is ensured and people get good service out of it. So the idea is to automate the testing process as much as possible in this case, so that the people at the Oslo City don't have to manually, for example, test the system, but they can do the system as automatic testing as possible. And the idea is to improve the quality of system. So again, in this case, we build this digital twin of a very complex testing infrastructure because you can see that they are like physical devices deployed at patients' home all over Oslo. They are connected also through the pharmacies, for example, to the hospital, to the general practitioner of each patient and so on. And this is the system we built to support automated testing because let's say I have to test 1,000 devices. I cannot borrow, for example, 1,000 devices and ask patients to run different kind of tests. So the approach we built is based on digital twins, which means that you can replicate as many devices as you want, and then you can run as many tests as you like. So the idea here was, so these are the digital twins, which are, in this case, I showed just one device, which, for example, it is about dispensing of medicine. In this case, then there is a testing approach, which is based on graphical user interface testing. And then we also have REST API-based testing approach that is built. So again, in this case, there are many machine learning components which we build to support this automated testing of these systems. And the idea again was, let's try to start replacing some of the machine learning components with the quantum machine learning components to see how these algorithms work in the real world condition, the real world systems and real world data. So we tried different algorithms, but in this particular presentation, I'm focusing on one type of machine learning, which is called extreme learning machine. So this is a classical version, and I will show you that how it is being converted into a quantum version. So for example, in this case, you can see that it's a very simple feed-forward neural network. And the classical data in this case is fed into this input layer like this way. And then you have the hidden layer where all the weights are fixed and usually randomly assigned. And then what happened is that based on this, on the last layer, which is on the output layer, you get the weights, and then you use those weights to train a simple linear regression model. So this is the different steps in the classical extreme learning machines are. So what happened in quantum extreme learning machine is that the first layer is replaced with encoder. And what is an encoder? It's a simple quantum circuit which basically maps the classical data into the quantum domain. And the main logic here is that when we can map this classical data into the higher dimensional data, we are able to identify the patterns which cannot be identified in some cases by a classical machine learning algorithm. And then once the data has been mapped into high-dimensional quantum data, in the next step is the quantum reservoir, which basically processes the encoded state. And then, since it's a quantum data, it's in a superposition states and so on, what we do is that we perform the read operations like this. We destroy the superposition, and then we read the qubits, and then we simply, okay, it's again, of course, not very simple here, depending on which basis do you read. So for example, here we can also use expectation values or simple z-basis reading and so on. And then again, very similar to the classical extreme learning machines, we apply a linear regression model on the weights and to predict the value of the target that we want to predict. So benefits are quite big that we can efficiently train a linear regression model as compared to classical one, and even with the less number of features, we can identify the patterns which might not be possible in some cases for a classical machine learning algorithm. So we run experiments on all these 3 case studies that I mentioned. So the first thing that we identified was that even with the fewer number of features, we were able to perform quite good. Actually, we outperformed with the maximum number of features. So for example, in Arona's case, the maximum features were 10, and with minimum features 3, we were able to reach the same performance, outperform actually with the 10 features, which means that even with the less features, it can identify certain patterns which were sufficient in our case. And then we also found that there were no significant differences between the classical and the quantum machine learning, which also give us a positive results about using this particular type of quantum machine learning algorithm. And in one of our case, even the quantum machine learning algorithm outperformed the classical machine learning algorithm. So these were the results on the ideal simulators with different number of qubits and so on. But then we also wanted to see how it works on the real quantum computers and also on their noisy simulators. So we tried different configurations depending on the hardware restrictions that we have. So for example, configuration 1, that we trained machine learning algorithm on the ideal simulators, and then we tested on the noisy simulator and the quantum computer. Configuration 2 was that we trained and tested in the noisy conditions. And then in the third configuration, we trained on the ideal simulator, but we tested on noisy combined with error mitigation approaches. And the fourth configuration is both of them on noisy plus mitigation for training as well as for testing. And in this particular case, we also tried these 2 error mitigation method, one is ZNE from IBM, and the second one is our in-house approach that we built, which is classical machine learning based error mitigation approach called QLEAR. So what are the results? First of all, we found that they did struggle with noise a bit, and which I think was affecting their performance in this case. And we found that when we add the noise in the ML training process, it helped QLMs a bit to deal with the noise. So which means that it helps a bit. And then we also found that even integrating error mitigation methods such as ZNE and this machine learning based error mitigation helped quantum extreme learning even a bit further. We also found that non-ML based methods such as ZNE were very restricted by the qubit size and the noise model that we're using. And we also found that the machine learning methods such as QLEAR, they excel in performing the machine learning classification tasks. They were good, but with regression, they were having some struggle. So in general, we found that QLMs are performing quite good, but they have some performance being affected by noise. So it means we want to build new methods to deal with noise so that they can work better under noise and the real quantum computers as well. So the way forward, so in terms of QELMs, we see that they have shown promising results in 1 industrial and 2 real-world societal applications based on the real data. But we found that we still need more work to improve their performance, especially when we are trying to use them on the real quantum computers. In this particular case, we tried only IBM's quantum computers. We didn't try others. But that's another thing we want to try, to how these will work on different technologies. And in terms of quantum AI, I would say that there are many opportunities. In this case, we only work with one algorithm, but we are also trying quantum neural networks, quantum, and so on, so that with the real world application to see that how those work in the real cases. And other things that we are working in my department are autonomous vessels, because if you know, the maritime is a quite big business in Norway. So our aim is to also see how they can help in autonomous vessels case. We're also working with Cancer Registry of Norway because they have collected a lot of these mammography images. And our idea is to apply quantum machine learning techniques to try to identify breast cancer sooner than it's possible with classical machine learning algorithms. And we're also working with Norway's oil fund. If you know that Norway has a quite big oil fund, and which is managed by one of the bank. And we are also working with them to look into different finance applications. And we are also looking into other applications of quantum machine learning algorithms. And we are also working on more foundational aspect of quantum machine learning so that we can improve the performance of the existing one. And we want to do that based on the knowledge that we gain by applying these algorithms into the real world application, to see what challenges we face when we apply them into industrial applications or real world applications. So with this, I will conclude my presentation, and I would like to thank National Institute of Informatics in Tokyo. They were part of all of the works that I presented, and also Mondragon University in Spain, and our industrial partners and real world case study provider from public sector in Norway Cancer Registry and Oslo City. Thank you very much.